Today's first lecture and 22nd lecture of this series is on Space Robotics in Future Science Exploration by Professor Rohan Paul, IIT Delhi. We have with us Dr. Piyush Chanana to moderate the session. I would like to introduce the moderator. Dr. Piyush holds a PhD from the School of Information Technology at IIT Delhi. He is a renowned expert in the area of embedded systems, user-centric design, and has translated several technologies from the lab to end users, particularly for the differently abled. His experience is wide-ranging from academia, industry, and non-profit sectors. With this, I am passing over to Dr. Piyush to introduce the speaker and to moderate the session.
Thank you, Dr. So good evening, everyone. So today we have with us Dr. Rohan Paul from Indian Institute of Technology, IIT Delhi, as a speaker. So he's Associate Professor at Department of Computer Science and Technology, and also a joint faculty member at Yardi School of Artificial Intelligence, and Associate Faculty Member at the School of Information Technology. Professor Paul's research interests include robotics, artificial intelligence, and assistive technologies, and his work has been widely recognized and published in various prestigious conferences and journals. So today he will share with us valuable insights on the topic of space robotics in future science exploration. So over to you, Professor Rohan Paul.
Okay. Thank you very much for a very generous introduction. It's a privilege to be here. At the outset, I would like to mention that ISRO is something that really inspires the nation, and the outstanding work that it has been doing in space exploration and India's space capabilities is known to everyone, and really fills everybody with a lot of energy and excitement. It is also important to mention that ISRO's technologies is not just about exploration, but they have byproduct applications ranging from understanding of the Earth itself, its own climate, as well as applications far-reaching as health and education, etc. For example, the satellites and other space-borne vehicles that are sent, they're able to connect various parts of the country, and educational messaging and many other parts of information. Any information which was earlier difficult is now provided through that. And also the early warning and many other pieces of geospatial work that ISRO does is again of tremendous values to everybody. Many of us don't realize that we touch pieces of ISRO technology at a very almost a daily basis. So I'm with that gratitude to ISRO and also to this initiative of trying to connect different technology fields with young minds and share ideas at scale. I begin my presentation. I work largely in the area of hardware design, embedded design, robotics, and now artificial intelligence as well. So I'll share some aspects of that with relevance to ISRO's mission. So this presentation is in two parts, and it's a short presentation so that gives us time for also interacting later. Initially, I'll talk about robotics and more generally embodied AI as an emerging technology which is going to have an impact in a variety of different areas, ranging from human assistance in homes to factories to space exploration. The applications are wide. Then after the brief introduction and sharing some work in this area, I'm going to turn attention to the specific things which are relevant to space exploration and space science. So I just want to double check, is the slide visible? Slide visible? Great, thank you. So let's begin with part one, which is on the topic of intelligent robotics. And what does this really mean, and how do we think of this in the emerging scenario of artificial intelligence? So the first point I would like to make is that if you look at our civilization and our own evolution, Our society has been propelled forward by our ability to affect the physical world towards things that we actually desire. Towards our objectives, we've been able to manipulate the physical world in a certain way. So if you go back to the agricultural age, when agriculture got transformed by implements, and the Indian civilization and many other civilizations as well show evidence that people used to make metal tools and use animals in a certain way to increase agricultural productivity. After that, what happened was the invention of the steam engine, and that led to the industrial age. And the steam engine suddenly made transport possible to large distances. It increased industrial production, and looms came up, many other production kinds of establishments started, and then the industrial revolution obviously began. Now, following which, more closer to our times is the electronic age, when computers are now becoming ubiquitous, and computers not just in the form of a desktop, but also these kinds of phones that we carry. They have a lot of computation which is happening. They are displaying information. They're allowing us to interact with information. They're allowing us to make a lot of calculations, and which is making our life really, really good. Now, if you go from the agricultural to industrial to electronics age, what has fundamentally happened is that our per unit ability to affect the physical world towards our objective has increased. Right? Now, the future extension for that is for intelligence aspect to not just reside on the computer, but also start residing in other either machines or systems that we interact with. And let us call this the age of the robotic age, or the age of embodied artificial intelligence. Now, one way to think of this would be that in the 1990s, when we had computers were large. They used to be kept in one particular place. We never had cell phones as well, and we never had smartwatches. Now, over time, computers became smaller. They got connected to better sensors, and now computers are everywhere. Computing is now pervasive. Right from our television screens to our watches to our phones to many other parts, computing has become pervasive. And the same thing is also going to happen, or is likely to happen, for artificial intelligence or any intelligent decision-making system as well. We're going to be interacting with intelligent systems all the time, and they're going to be assisting us. They're going to be increasing our productivity as we go along. So the modern way of thinking of robots is to think of this as more general embodied AI, which are intelligent agents capable of autonomous goal-directed behavior. Now, that means that they take input from the environment in terms of sensing, as in images or text or other forms of individual modalities. And on the other side, they interact with us, or they perform some kind of a action in the real world. Okay. So on the left-hand side, in some sense, you can think of this as traditional artificial intelligence, which is speech recognition or image captioning or many of the other newer things you're seeing, even ChatGPT. They all sort of lie on the left-hand side. When they are fused with the physical world in which we are living, or when they're interacting with us directly, then the fusion of these we call as embodied AI. Now let's take a specific example. And on the left-hand side, there is a picture of a robot. That robot is helping a soldier, let's say, handle a certain hazardous object. Okay, so for example, let's say, let's say some hazardous thing like an explosive or some other thing. The human does not want to go, but the machine is to be sent. Now, this particular machine, we can interact with it at a lower level. That means we can program every part. But let's imagine that in the future, we would like to have a machine which can do something like this. That we say, robot, secure a certain area. That means anything which is hazardous, you identify, you pick it up, you put it in a certain safe area, and then the task would be complete. That higher level ability to take a higher level instruction and then break it down, that's the capability that we are looking at. Now let's just turn this, just pause for a moment and just think that if our mother is saying the same thing in the kitchen, then how would we process this? For example, if she says that, let me, please get me the pickle. The pickle is somewhere in the cupboard. Please get me and put that on the dining table, right? Then we would think about where that pickle is. We need to go, operate it, pick it up, open it up, and place it in some other kind of place, right? So if you look at that example, which is closer to home, we can identify that there are certain cognitive functioning or cognitive processes which are operating, going from the top level instruction to something that the machine is doing in the real world. Okay, right. So now let's see that we have to understand the intent of the instruction. We should know what the world state is, and then we have to perform reasoning and planning, and then finally behavior execution is to take place. So there's a lot of intelligence which is built into our brains is going to come into place, right? And that is the technical scientific challenge of bridging this gap between what the human wants and what the machine can actually do. Now the machine may or may not be a physical robot. A lot of the times it will be, but it can also be a certain generic kind of a system that we're interacting with. Now, how do we model this kind of a system? As engineers, we are very good at block diagrams. So let's try to make a block diagram where we have the robot. The robot is going to take some information from the environment. Let's call that a state. And it is going to generate a plan, a sequence of actions that once executed in the environment are going to take the robot towards what the human was intending to do. So this is what is called a classic AI-based agent architecture, in which there's an agent that lives in the environment. It consumes observation and generates action, consumes observation, generates action, and then so on and so forth. It keeps proceeding all the time, right? Now let's take certain examples of this. These are certain examples from our lab, which give an idea about how these kinds of things can be realized. So on the left-hand side, you see there is a robot which has a ground base, and it has an arm, and it is able to pick objects either on the ground, on top of another object, or from inside from another object. So this is picking happening on the left-hand side. Below, you see placing of objects. The object that was picked up is put gracefully on the side. It is put gracefully on top of another object or also inside some other container. Right? Now, actions are low-level control routines, but they also have semantics associated. For example, you can pick an object only when there is nothing on top of it already, right? So if you say that there is some object here, there's something on top of it, I cannot pick up the lower object before having picked and removed the object on top of it. So there are certain preconditions and there are certain post conditions which are also there. Once an object is picked up, it is not there in its original position, and it is there in my hand, right? So these are the semantics that we also need to take into account when we're synthesizing long horizon tasks, when we compose these things into one another. Now, when you look at a machine of this kind, a robot of this kind, it's important to remember what all does it have. It has sensors, so it has cameras, it has LiDAR, it has an arm that can lift and then grab something. It has wheels. And also there is a small computer, which is the brain, where the intelligence software is running. Typically, it's an embedded computer, an embedded system on which this intelligence is being encoded. Now with this, let's consider the example of a robot being asked to clear the debris in front of it. So there are certain objects which are there, and we want the robot to actually pick it up and move it away, right? So, so let's say the robot actually wakes up. Okay, so this is robot's hand. It is picking. It is going to a certain position, and the cameras on the hand are looking downwards, and they're trying to identify what all objects are there. So after that, once it does some visual scanning, it'll know that there is a pipe and there is a box in front. Then it recognizes it and also tells that I have these objects in front of me. And then the human commander is going to then say that, okay, search for objects in the front, and then finally clear the objects. So now the robot is waking up, it's looking at its surrounding, building a model of what all objects are there, and then it will start interacting with it. Okay, so I'll see this like a child, there's a visual surveying. Let's say in the kitchen, you want to find a pickle bottle. So then you'll go and then you say, I found some object. So here it said that it had a case and a pipe in front. And then it will be asked to clear the object, clear the objects in front. And when that happens, clear the front, it is going to synthesize some sub-actions, which is going close to an object, picking it up, picking up another object, so on and so forth. It will break down that task and then start fulfilling it. Okay, this task is called planning, which is sequencing of smaller level actions one after the other, so that the larger, temporally extended action can actually be performed. Okay, so it picks this object, it can put it on the side, it can put it on the other vehicle on the left-hand side, and so on and so forth. Right. So from atomic sequences of low-level controllers, we get the ability to think of action at a semantic level and can compose them one after the other. Right. So it's putting this on the side. Now, if I fast forward this video, then it'll also pick up the pipe. So it's picking up the pipe, and then it'll gracefully pick up the pipe and put it on the side, right? This kind of a clearing has happened. Okay, so what we're able to see is this ability to go from language to certain high-level intent to objects being picked up and put on the side, right? Now let's look at another example where there's also navigation involved. Okay, so let's say a robot has to go behind a barrier and see if there is something suspicious lying there. So you saw that there was a barrier and there were some objects on the side of it, and the robot is unaware of that object. So the robot is asked to search behind the barrier. So now it will start moving. It avoids certain objects, right? And it will go behind that particular barrier. So once it goes, it's you will see it being behind. Once it reaches behind, it's going to double check that is it really behind or not. Okay, so it will say that, okay, from here it will raise its hand and then check that I'm actually close to or behind the object, which is the wall, and then I can start executing the exploration actions like what is there on the ground, etc., etc. Right, so some of this research has been motivated by assisting soldiers who need to explore dangerous areas. So you would like to actually explore a certain area before the soldier goes. So these kinds of technologies are built for that kind of a application. But the core is that there is now exploration. The robot can actually explicitly go behind a certain area, find objects, and then proceed accordingly. Right? Now there should be some questions in your mind. The question would be, let's say, how does a machine actually see the world? So the machine sees its world through sensors. So this is LiDAR sensors, which are essentially a laser beam which is sent, and that laser beam hits certain objects and then tells if there is a certain object present there or not. And by this hitting, if you accumulate them, you get something like a map. So here the robot is moving around and it's getting these laser scans, and with that it is able to fuse and get information about the geometry. So this is from a lab, so it is inside the lab, then it moves around, then it goes outside, and then it's able to get information from other parts and build a coherent large-scale map of the environment. Now notice that this is what the machine will now think about the geometry of the environment in which it is operating. And once it has built a map, it can be asked to go from one location to another location, right? Then it can start saying that, okay, I'm going to move in this particular way and then go in this other direction, right? Now LiDARs have certain advantages. They, unlike cameras, can see in the dark. They're not affected by dark because they're sending a certain laser beam on this, right? So they are good to understand the higher level 3D structures. Now you get the 3D map of this entire, our lab is only this part. Now we'll be able to construct the map of the entire area. And this map itself can be useful, but it's also useful for the robot to navigate, right? Cameras everybody knows about, so I'm not going to talk about it. These are sensors that look at the environment, get some information about colors and so on, and then we can perform the optical processing from this. Okay. The other aspect about intelligence that I would like to highlight is the fact that the agent is interacting in the environment, right? So robots have the capability to fiddle with objects and then build their model. What is their geometry? What is their appearance? Where are they kept? Can I push them away? So a lot of probing can happen, which is a form of exploration. So on the left-hand side, you're seeing two robot arms taking an object and then manipulating it, building a model. On the right-hand side, you'll see a robot which is going to push away a certain object. Now this object, its mass and other properties are not known. So what does the robot do? So the robot will actually make contact with the object, right? Just fast forward it. And then, like a child, it is going to try a little bit with different force values to try and move it, to see whether it's even movable or not. Once it is actually able to overcome that friction, static friction, then it can execute in the dynamic phase and then complete the task. Okay? So this is probing. Initially, it did not know what is the mass, can it even move, and so on and so forth. and then it tries to push a little bit further and then get the exact information on this. Okay. Right? Everyone with me? Now let's turn our attention to even higher order thinking or higher order reasoning. Okay. So on the left-hand side, now we're talking about human collaboration, where there are certain objects in front of the robot, and we would like the robot to hand over certain objects to me. Right? So there's a human here, and the human says, "Bring the green colored towel to me," and the towel is somewhere here. Right? So the robot scans and then is going to then pick up the towel, picks it up, and then finally delivers it to the human's hand. So it was able to detect the human, what all objects are there. It is able to understand this high level instruction and then finish the particular instruction. Right? So in some sense, it performed a spatial reasoning. That means higher order understanding about objects in its environment, and then pick up that object and place it in some other location. Now let's see the same thing, spatial reasoning operating in time domain. Right? So on the right hand side, you're going to see my colleague Nadir, who's going to bring different bottles and put one bottle, the second bottle, and the third bottle on the shelf. And he's going to go away. The robot is watching. Now another person comes in, another colleague, who says, "Give me the bottle that was placed second by the person." And see the bottle that it is going for. There are 3 bottles. It figures out the one that was placed second. That means this has the ability to maintain some kind of a memory. It can go back in time and reason about when certain interactions have happened. And with those interactions, it is effective to figure out that this is the bottle that you needed. Right? Now, this is really interesting. This gives the ability for the machine to see what is happening and then respond appropriately, even when there is a change of the person. So on the left-hand side, you see spatial. On the right-hand side, you see extension to temporal reasoning taking place. Right? So these are little snippets of what this technology or this emerging technology is. I would like to mention that what is happening here is some form of object detection and scene representation. That means there's an AI system which recognizes certain objects in an image and stores where their location is. Now, when we ask for a certain object to be retrieved, then the robot is able to figure out that this is the object in a certain area that is to be picked up, and it is going to be put in a certain different size. So that's the object recognition or visual recognition, and the camera is there on the hand, right? Like we also have a neck, we have a head, and we can look around, and then we can do certain interactions. Similarly, the machine also is equipped with these kinds of sensors. It also has a mic, it also has acoustic sensors, and it can speak and it can communicate bidirectionally to it. Some of these have been motivated by assistive applications. So in the future, these machines are going to be in our homes, they're going to be in our hospitals. They're going to be caring for, let's say, people who cannot move on their own. They'll be looking after the elderly or people with disabilities, right? So these technologies are being invented for that kind of an application. But there is this fundamental thing about human-machine interaction, which is what we are trying to build. Now I'm complete with the first part. Now I'll briefly talk about the relevance to the space program of some of these technologies, right? Now these are broad technologies. They can have an impact in assistive domain, manufacturing domain, educational domain, many other domains. But today let's talk about space science and the exciting applications there. So one of the most exciting things here is that space is an unforgiving environment. Okay, it's it's near vacuum. It's inhospitable conditions, and robotic explorers is the way that exploration is going to happen in the space. And if you are aware of the recent missions being planned for the Gaganyaan mission, which is going to send an astronaut into the orbit and into space, preceding to those missions, there are going to be 3 unmanned missions which are going to take place. So this is a humanoid robot called Vyomvitra, which is being developed by IIRS-ISRO, and that has a humanoid torso. It has a head, it has hands, etc. And these hands are human-like. Okay, so they can actually touch a panel, they can see a certain display, and they can read what the display is. So they are AI-powered as well. And this machine is going to basically first collect data that is the flight and the environment even safe for humans. It is going to give that kind of a information. So before going to a dangerous kind of an environment, the machine goes first, and it is going to generate all this data, and it is going to help us eventually plan these missions further, right? So this is under development, and this year, hopefully, we will see this getting launched to space. Similarly, recently in the last the mission, the SpaceX mission, where there was a docking of 2 satellites that was attempted, there was another series of experiments which were carried out as POEM. So as part of POEM, what was demonstrated was an indigenously developed arm like this, which was moving around in the blackness of space. Okay, so the arm basically lifted and then moved to different positions. And this is the first demonstration for a space robot happening from India. So this is very exciting. Now, this has many applications. This can be used to examine the exterior of a spacecraft, whether there is some damage or what is the condition outside the spacecraft. Okay, it can also perform some kinds of repairs. Okay, in the future, maybe it can repair a certain kinds of things which are very hard to do. You'll have to send somebody there, and that's very dangerous. Can the machine actually do that for us? Maybe a solar panel or assess damage or replace or reinforce or things of that kind, right? And third is actually capture of a satellite, right? So if there's something which is actually adversarial or not in control, maybe can you capture that kind of a satellite? Or even if it's a normal satellite, can you capture it, then replace some parts of it, and then send that back into orbit? Some kind of orbital servicing is likely to be the next generation of this technology is going to lead into that direction. Okay, but this is very exciting. This is actually operating in space, and this is very interesting thing. Okay, so in future there are other countries that have been working on this kind of technology, and they're also exploring different concepts. For example, this is an arm which is helping an astronaut explore the outside in a spacewalk environment that is being done. This is some concept for satellite capture and then doing operations with it. And typically these are extravehicular operations, and the astronaut from inside has the ability to control the robot outside through a certain kind of an interface, which is a joystick kind of control is there, and then you can control that, right? So the human is always there. Okay, so the machine may be operating in a certain way, but the human is guiding it or controlling it, right? So the human aspect is always there in these kinds of systems. Now let's turn our attention to traditional exploration. Okay, so let's turn to space exploration on extraterrestrial surfaces. So almost everyone has seen the ISRO's Pragyan rover that was that descended down from the Vikram lander and was exploring the south pole of the moon surface, right? And you saw that rover came down, and then it collected data, it performed some kinds of experiments, and it relayed information for scientists for analyzing, right? So this is something, again, we have not been able to go to the terrestrial body ourselves, but we can send these robotic explorers, and they can do science for us. They can study mineral composition, they can explore what the environment conditions are. And because moon does not have an atmosphere, then it has different conditions in the sense that the sun does shine differently on this separate body, and it gives some cues about how the solar system itself was formed. Now we can send people have been sending, different agencies have been sending robotic explorers to different places. So ISRO also has sent to Aditya L1 mission, which was a mission to the sun. Essentially, it's orbiting the sun in a certain, certain kind of an orbit. There are certain additional details about Lagrangian points and those other things, but these are special orbits where you can actually monitor the sun, because we are always affected by the sun, right? If the sun's internal processes change, they have an impact on communication, they have an impact on our climate, and in general, the sun is obviously very important for life on Earth as well, right? Now, let's say Japan has sent a spacecraft on asteroids, and they're studying different properties of asteroids. Asteroids are small bodies, they reside in certain different parts of the solar system, and they've not been studied, and they're rich in minerals, and maybe we can extract minerals one day by this kind of a technology. And obviously others like developed world, US, and many others have been sending. So this is Mars Science Lab, which was an entire rover with almost like a chemistry lab on board, which was sent on the Martian surface to study different properties, look for water, and many other kinds of things, right? So these kinds of things are there, and typically where the technology is progressing now is increasing the ability to do physical interaction. That means digging or surface operation, or maybe in future when the astronauts need to go, the preliminary work in terms of paving the soil, doing some kind of habitat construction, performing initial experiments would be done by robots, then astronauts would come in, there would be certain operations. When the astronauts leave, then the remaining science experiments will be carried out by these kinds of machines operating over a long time. And that's where the vision is, right? So here, new technologies currently in R&D phase, which are being developed in different parts of the world. On the left-hand side, you see scooping. So certain scooping operation is being done by lifting the soil, putting in a container, and then trying to bring it back. Let's say for a sample and return mission or for chemical analysis within the rover itself. Here you're collecting rock samples, picking them up because they have geology and many other things. And let's say a bimanual operation, two arms which come and do some kind of a construction sort of remotely on a different surface, which is there, right? So this is where eventually technology is going to go. Great. So I think at this point, I will try and conclude. So the two parts that we discussed was about intelligent robotics, that is machines that are AI powered and have the ability to understand human intent, understand the environment, do some kind of a reasoning and interact with the environment, right? And for space, there are many applications. The applications on space station environments, right? For extravehicular, but also inside. Maybe inside the, India is going to have the Bharatiya Antariksh Station, where there are going to be experiments that are going to be done inside. And again, robots are being developed for that, for even the intravehicular activity. Extravehicular, we've already discussed, right? Then extraterrestrial operations on different surfaces which are there. And I think that is going to add tremendous value to space science. And in the future, when humans are able to travel to other places, then some of the preparation and also continuation of human experiments would be carried out by robotic platforms, and that's where the technology is going. Right. So at that point, I will stop the presentation, and if there are questions, I can take the questions at this time.
Thanks, Professor Paul, for the wonderful talk. It was really exciting and insightful. Let us wait for a few seconds for any questions from the viewers. Okay, so first question has come from Shriyanka P. How much maximum lifetime of a robot?
Okay, so just a second. I'll mute Kalam. Okay, so what is the lifetime of robots, right? So again, that is an important part that we need to take into account. So the experiments that we showed in the lab are mostly for technology that is still being developed, right? So there the focus is on demonstrating, and these are not hardened for the environment, but there is enough understanding about the environment in space and the environment in the launch conditions. When the launch happens, there's a lot of force that gets exerted. So that kind of a hardening would need to be done. And that is still a challenge. So there's a lot of interfacing with the material scientists and manufacturing engineers that need to be done in order to make this robustified, right? But seeing that India is able to perform experiments in space through robotic arms, that gives us some confidence that eventually this technology will get developed. Similarly, the apparatus that was sent on the moon, it functioned for a small time, maybe still functioning, but for long-term operation, it has to be sort of engineered. And I want to say here that the battery is a main challenge. Power is a main challenge in these kinds of systems. So it's not just the robot mechanism, but the battery and finding energy is going to be a challenge.
Next question is from. Can you mute? Okay, next question is from Mr. Ravi. How can we design robots to operate autonomously in extreme conditions?
So the central principle here is that the robot needs to be extreme and unknown conditions. I would add that. And unknown mathematically means that the distribution through which the state is going to come is going to be either very large or not known to us. Okay, so you can think of this as a stochastic process in which the agent gets a state, and the state it has to decide an action. Now the state can be sampled from a very large distribution, and that's what extreme and that kind of a thing is. So mathematically, our design of algorithms need to account for uncertainty. They need to have contingency. That is, something does not work. If my wheel gets stuck, then I can recover from it. So a lot of higher order reasoning is to be done. For example, if I'm not able to pick up the pickle bottle, then I will climb over somewhere. If the pickle bottle starts falling from my hand, then I'm going to clasp it more strongly, right? So that adaptation I'm going to do. So these kinds of things come in, and that is where the algorithms are really, really challenging. You have to do a lot of thinking, and the robustness has to be accounted for. And as engineers, I think we like challenges. So I think we have to design algorithms in that particular way.
Last two questions. One is from Nivitha. How Vyomitra is different from other robots, and how it can help astronauts and also for other research works.
So the Vyomitra is a humanoid. The humanoid takes inspiration from the human form. That means it has a chest area. It has two arms. Okay, it has hands which are dexterous. That means it has fingers and other things, and it can also see. It can speak. Right. So in some sense, it is a digital twin of an astronaut. Okay, so it is different from a rover because the rover has to operate under surface condition and has to do specific tasks. The humanoid is going to do a little bit more of this. Secondly, it's going to absorb sensing. It is going to take sensory input and see what the displays are, what is the condition of the interior of the spacecraft, and it is basically a human proxy. So once the spaceship goes into the orbit, things may be okay, may not be okay. We hope that everything will be okay, but it has to check whether everything is going okay, right? Second is going to touch and change the status of the switch. It is going to operate certain switches, and it is going to give basically the right flavor of testing before humans are going to be sent. So the objective is different. One is science, but here it is human science and also human safety, which is going to be done.
Last question is an interesting one from Urmi. Could space robots use musical frequencies or harmonic tones like ohm-like signals as a universal medium to stimulate responses from alien ecosystem?
So I think this is exciting. So I would say that humans are multimodal, right? We see, we speak, we hear, and I think future robots going to other places will be listening, or they might be actually producing some kinds of sounds as well. Now the environments in which they're operating may or may not have atmosphere, so we may not be able to have a conversation as yet. But as pieces of technology, they're also beacons for anybody who wants to listen. So for example, if there are spacecrafts like Voyagers, etc., which continuously transmit some kind of information to others who may listen, and no one knows if we are alone or there are other species as well. And maybe they see the presence of these things and they try to communicate with us. But they have certain imprint of our civilization in them. They carry our engineering, they carry our data and any other things, and it is they are just as, let's say, a visitor comes and we give them something about our culture or civilization. Similarly, as humanity, these are our in some sense our representatives or some kinds to outer worlds. So I don't know whether actively we can do anything because we don't know about their existence and many other things. But at least passively, whatever it is doing, it will be a reflection of our humanity in totality.
Thank you very much for answering all the questions. Okay, so back to the ISRO Control Center.
Thank you, Dr. Piyusha, for well moderating the session. Also, our sincere thanks to Professor Rohan Paul for providing an insightful and informative lecture. Thank you once again for supporting the START 2025 program. Possibilities by Professor Aloke Kumar, Indian Institute of Science, Bangalore. our speaker and moderator to join. We will start the session very soon. So dear participants, now we are going to hear the next lecture on building structures on the moon, challenges and possibilities by Professor Aloke Kumar, Indian Institute of Science, Bangalore. We have with us Sri Aloke Jadhav to moderate this session. I would briefly introduce the moderator. Sri Aloke is an industrial design graduate from the National Institute of Design, Ahmedabad. He is keen on working with computational design, systems thinking, and interactive immersive experiences. Currently, he is working on Professor Aloke's team to develop India's first extraterrestrial habitat. Over to Sri Aloke.
Thank you, Dr. Praveen. I will quickly introduce Dr. Aloke Kumar. Dr. Aloke Kumar received his bachelor's and master's degree from the Indian Institute of Science, Indian Institute of Technology, Kharagpur, India in 2005, and his PhD in mechanical engineering from Purdue University, West Lafayette, USA in 2010. Dr. Kumar joined University of Alberta's Mechanical Engineering Department in 2013, where he was the Canada Research Chair in microfluidics for biological systems. He moved to the Indian Institute of Science in 2017, where he has re-established his lab with a focus on space technologies and manufacturing in space. Currently, his lab is innovating for the space age with a vision of advancing India's contribution to space development and establishing our first permanent settlement on extraterrestrial planets. A very good afternoon to everyone. I'll hand over the lecture to Dr. Aloke.
Thank you, Amok. Thank you very much. Just confirm that you can hear me once.
Yes, we can hear you.
Great, thank you. Okay, welcome everybody. I guess you've had one lecture before, and they've had quite a few lectures. So I hope you've been enjoying the START program. And first and foremost, I think this is a fantastic initiative that ISRO is undertaking, and I'm very happy to be a part of this. So thanks to ISRO for inviting me to this. And as the lecture title suggests, I'll be talking about this building structures for extraterrestrial environments. It's obviously a very extensive topic. There's a lot of things happening and a lot more things that will happen in the future. But I'll give you a glimpse of some of the things that are happening. Obviously, we cannot discuss everything on this particular topic now, but at least by the end of this, hopefully you would have gotten some glimpse of what challenges are there and what possibilities exist. So let's get started. If you, okay, I think there is a little bit of a lag between, Amog, has it gone to the second slide?
It hasn't yet. It is frozen on the first slide for me.
Okay, just give it a second.
Yeah, I can see it.
Yeah, great. Okay, so the photo that you see on the left-hand side of this was a photo taken by me at Rakhigari. This is if you can see, there are these brick structures here. This is part of the first one of the first cities that humanity built on this planet, part of the Mohenjo-daro Harappa civilization, or as others now have said that this is part of the Indus-Saraswati civilization. And these were the first houses, one of the first houses that our ancestors built. So, in some sense, this brick, the brick that you see today that ASI and others are uncovering in northern India, these are the first fundamental building blocks of the human habitats. So to build these first cities, humans used a material that was abundant, and that's soil, right? Soil was the most abundant material that was there. And it turns out that the top, so the technical name for, so let's say you have a planet and then you have the top layer, and then you obviously have the core at the center, then you have the mantle layers and others. But the top of the surface, which contains, let's say, this weathered and fragmented soil, rocks and sediments, etc. This is the technical name for that is regolith. Okay, so instead of calling it soil, we'll call it by the technical name regolith, and we'll see why we need that. And this is a reference for this particular definition if you ever want it. Basically, it is the fine powdery material that is there on the surface of a planet or a surface of a structure like moon. It does not refer to structures like hills, valleys, etc. Large geological structures, it doesn't represent that. It doesn't represent the core of the planet also, and it doesn't represent any other thing. It's just the fine powdery thing that is there on the surface. We'll get a little bit more idea of what regolith is by seeing this second photograph. I hope you can see this particular photograph. You can see here, this is the footprint of the first Apollo astronaut, Neil Armstrong, on the moon, and this is taken from the NASA's website, and it said on the website, it is instructive to read, that the first footprints on the moon will be there for 1 million years. There is no wind to blow them away. So on the moon, there is no atmosphere, and you have this fine powdery material. This powdery material is the regolith. In the regolith, you can see this footprint of the astronaut. Right? So so you can be a little bit more clear on what this regolith is the sandy structure, sandy upper layer of a surface of a planetary body. So now we know that this regolith exists, but on the moon you have a lot of challenges, right? Yeah, there's a bit of a lag between my changing the slides here, and yeah. So moon, let's take a look at it. It's a slightly alien world to us. It has no atmosphere. Okay, volatile molecules have been detected, but that doesn't mean there are this is an atmosphere. Volatile molecules like water, etc. But that doesn't give an atmosphere. It's very sparse. Extreme temperature variations from searing heat to chilling cold. If you've known, it is approximately, it goes from minus 200 degrees Celsius to plus 100 degrees Celsius, approximately in that range. And that's a huge variation of temperature that happens. There is no magnetic field and no atmosphere, no protection from radiation. It also has 1/6 of Earth's gravity. So these are all challenges for any structure to be made on the moon. What are the advantages? Well, we don't have our standard bureaucracy there. You don't have to fill out a lot of forms for making structures, right? So you don't have to submit something in triplicate at different offices and get permission again and again. That's just a small joke, but you know, to figure out how to make things on moon, we also have to understand, is it truly an alien world? Right, all these challenges that I've written here on the left, these show that none of these things are like Earth. So what is it that is like Earth? Now, to understand that, we have to go back to the theories of what moon, and the giant impact hypothesis says that perhaps a big object came and collided with Earth, and all this debris got strewn, and then this debris coalesced in the form of a moon, and it also fell on the surface of Earth, right? So what happens is the moon is not completely alien. In some sense, it's part of us because it collided with us. It shared materials. Materials were flung out, and some of it fell on Earth, some of it coalesced, and vaporized debris became the moon. And there are similarities. That's what you would expect from this theory. It turns out it is actually true. It so happens that the moon and Earth, they share a history together, and because of this, they share a lot of there are geological similarity. So what happens is there are certain types of rocks called anorthosite rocks. They are very similar to the rocks and sand that are found on the moon. Now, it so happens that on Earth, we have a deposit of anorthosite in Salem, Tamil Nadu. Okay. There is a mine there, and the mines that you this is the type of white rock that you find there. If you take this rock and if you pulverize it into small fine grain, and this is what this grain is going to look like. I have taken these pictures out of these two papers from ISRO that were published. These people were some of the pioneers who developed this lunar sand simulant. You see, if you want to create structures on Earth, we have to use material that is like the moon, but not obviously from the moon. So what they found is these mines from Tamil Nadu, they have these they have these rocks which are very similar to the rocks on moon. They took them, they powdered it, and now you have this moon's regolith simulant. Okay, simulant. So it is important to understand that these are simulants. So we are simulating the actual material that is found on the moon. Now they also did a very nice comparison of what is there on the moon versus what is the what are the contents of the simulant. So it turns out that the simulant or even the moon rock primarily consists of SiO2, which is sand. I hope you remember some of your high school things where SiO2, which is basically sand. Let me, yeah, now it's here. So this is the primary constituent of it. There are some oxides like aluminum oxide, calcium oxide, and others, which are less than the majority participants. The majority is silicon dioxide, sand, and others are minority participants in this. So what you can now do is you can go to Salem. You know that Earth and the Moon formed had some similarity or some past shared history, because of which there are rocks on Earth that are similar to that of what are found on the moon. You can go and find them, and you can bring them to the lab, and you can create these moon regolith simulants. The good thing about them is now that you have them in the lab, you can start doing some experiments together, right? Now, we took some of this regolith, and I'm just waiting for this thing to update it. Oh, there it is. So if you take the same regolith and if you put it under a scanning electron microscope, this is what it looks like, okay? The lunar regolith. And you can also do complex studies, like this is an XRD pattern of the lunar regolith, and you can see these different peaks. They represent the different elements and the different amounts of this element that are there. You can see that these are not nice round shaped. These are obviously jagged shaped, and this is what you would expect. But we had this rock that we had this thing in our lab. Now, what we wanted to do is we wanted to make bricks out of it, just like our ancestors had done long ago. So we wanted to explore more sustainable techniques for doing that. Now, it turns out that there is a process called MICP, which actually stands for microbial induced calcite precipitation. You can see this process here in the bottom. This is a bacteria. This green thing right here is a bacteria, and you can see this blue object, right? This is actually calcium carbonate, and there are certain types of bacteria, certain very specific species called the ureolytic bacteria, which can take urea and calcium, and through a process called ureolysis, there's a complex chain of reactions here which are not fully shown, but you end up with this calcium carbonate formation, which is what you are seeing here. There are other processes also. I'm not going into all of that. We use this particular process called the ureolytic bacteria, which performs ureolysis, and it can precipitate calcium carbonate. Now what happens is this bacteria, the reason we took it is it is there in Earth's soil, and it exists in very large quantities in the Earth soil, and it helps bind the structure of Earth soil together. Because you can see this golden thing here. These are biopolymers that the bacteria secretes, and what it does is when the bacteria is in the soil, it helps bind the soil together. So we were quite interested in this thing, and so this process obviously gave us some ideas for making bricks outside. So what we did is we we got this bacteria into the lab, and we put it into a small cuvette, and you can see this here you have the liquid plus bacteria. Here you can't see the bacteria, obviously it's very small. This is bacteria plus the food that has been given. So when the bacteria is food, the right food, it results in a precipitation of calcium carbonate in the system. Okay. And this is here, this is a scanning electron microscope image on the left, but this is what you see in the lab with your, if you want to look with your own eyes, this is what you will see. Again, if you put it under a microscope, this is what you find, and you can see these nice bacterial polymers. These are the bacteria right here, and this is calcium carbonate, this long, big object here. So we know that with this particular process, the bacteria, when it is mixed with earth soil, it can lead to strong consolidation of the soil, and it sort of hardens in the form of a brick. So we said, okay, why not try that also with the lunar soil? Let's see what happens. So what we did is we took this bacteria and this specific particular microbe that can participate in this process, and okay, so and we mix it with our lunar soils. Okay, so bacteria plus lunar regolith. These are obviously lunar regolith simulants that we had used in the lab, and when you mix them, it actually forms a slurry. Okay, I mean, this is just an example image of a slurry. This is obviously concrete being poured, but this is what a slurry looks like. It's almost solid, but it also flows like a liquid. That's what a slurry is. So when bacteria is mixed with this lunar soil, it forms a slurry. Slurry is a state of matter that is in between a fluid and a solid. Okay. So with this, what we did is we were able to put it into these casts, and we poured this lunar soil simulant into these small casts. And for example, we put it through an aluminum block. Then we poured this soil into these casting structures. This is a normal casting process. And then we incubated it for 5 days, right? Incubation for 5 days. This is almost like cooking. At house, you cook. So we just put this incubator, and this is put at room temperature, by the way. So this is basically also not cooking. We just leave it out there. And we return after 5 days. What did we see? Well, we got this consolidated structure, but in the beginning, this consolidated structure broke. Yeah, and it was very, very weak, which surprised us. And we kept trying this for 2 years because this bacteria, when grown in earth soil, grows very well. And it leads to very, very hard rock, brick-like structure. So if I do the same experiment with earth soil, it forms this really nice, hard brick-like structures, but not with the lunar soil. So we kept trying and we kept failing, which made us feel that there must be something wrong or something missing in this entire thing. And actually that was true. What was happening, I mean, you have seen this, the lunar soil, right? Now the lunar soil is not, if you remember, if you go back to this particular slide, you can see that the lunar soil is very rough, right? In the scanning electron microscope image, you could see. And by the way, I mean, these kind of things like silicon dioxide, aluminum, etc., these are also present in the earth soil, but there is something missing. There is something there is earth soil that is not there on the moon. You know what that is? That is a clay. There is no clay on the moon. It is sand. This white powdery thing that you are seeing here, this is the old rover, by the way, that is being tested at ISRO. There is no clay over there. And clay, as we know, is an important constituent for retaining fluid, right? So because there is no clay on moon, so bacteria were dying. So now obviously you cannot take so much clay with yourself, and that became a big problem. Bacteria were not surviving in the lunar sand. So then we said, okay, maybe can we use something like guar? Guar is a powder, is a fruit that you grow in northern India that grows in large quantities. This fruit, when you dry it and then you powder it, it becomes this powdery substance, like here it is shown, right? And this powdery substance, when you mix it with water, it dissolves very quickly and it results in a biopolymer. And we decided, okay, if the bacteria, we have to help the bacteria in some way. We cannot give clay because clay is present in very, very large quantities in the Earth's environment. But we said, okay, we will put very small amounts, less than 1% of this guar gum into this clay structure. So if you are creating 100 kgs of this slurry, you will put only 1 kg of this guar gum there, or less than that. And when we did that, the bacteria started growing very, very well. And what you got is you got this really, really nice brick-like structures. So you remember the casts we were showing. So this is a nice, it's a cube-like structure. You can't see at the top. There are forces being applied from the top and the bottom. So it is being compressed. Okay. And this is to determine experimentally a compressive strength. So I'll just play this in a video, and we apply compressive strength on this brick-like structure. And you can see now that there's a crack that has grown, right? So if you apply too much force, this brick-like thing breaks. So we studied the compressive strength for this, and when you have just the bacteria plus this SP is the name of the bacteria. LSS is, by the way, the lunar soil simulant. SP is the name of the bacteria. When you just have the lunar soil simulant and the bacteria, the compressive strength is very low. So it's of the order of some kilopascals. Kilopascals, by the way, just to give you an idea, it's weak enough that I can break with my own hand. Okay, it's like bread, so hardened bread that you can break. This now we added on the lunar soil simulant, we had the bacteria now, and we added this bit of a guar gum, right? And when we tested that, we found that the compressive strength was of the order of 2.5 megapascal to almost 3 megapascal. Now, just to put this into perspective, around ice is of the order of 5 megapascal, 5 higher sometimes, depending on the temperature, around 5-6 megapascals. So 2.5 is not bad. It's almost like half of ice. And with ice, you can make igloos, right? So on what did we learn about gravity on Moon? It's 1/6. So this compressive strength is good enough to start making houses with this kind of bricks. And by the way, if any of you want to read the paper on this, this is the particular paper. You can find it. If you want a copy and you cannot get it, you let me know. I'll get it for you. These bricks were strong enough that we actually put it, by the way, I mean, if any of you are from mechanical engineering or you have gone to a machine shop, you'd recognize this. This is a lathe. This is the mounting chuck. And this is the brick when it comes out from our mold. This is a cylindrical form, and we have put a cutting tool here. Okay, and I just wanted to show you how hard and how strong these are. So this is metal, right? This cutting tool here is a metal. It's becoming fine powdery like substance. So now these bricks are strong enough that it could be shaped and be made dimensionally precise. These things, we called it them to be space bricks. By the way, your typical house brick, okay, typical house brick is usually somewhere between 5 to 20 megapascals strength. Okay. Megapascals is the SI unit. Mega is 10 to the power 6. Pascal is the SI unit of pressure. So this is 5 megapascals is the compressive strength of this particular type of brick, the whole house brick. But we had reached some 2.5. This particular research, as you saw, this was published quite long ago. It was 2021. Actually, the work was done even earlier. It took us some time to publish that work. Since then, we have done a lot more work where we have manufactured in many different ways. So we have explored 3D printing. Unfortunately, because of the lack of time, I'm not going into all details. I've been told we were given 30-minute lecture time, so I wanted to keep to that. We have done 3D printing with this slurry, whatever you saw. We have used different type of binders, and they have worked out very, very well. We have tried different types of casting. We have also tried sintering. Okay, in sintering, we have tried furnace sintering. Sintering is a technique where you make bricks by heating them together. So you put this brick like this cast into an oven, and the oven goes to a very high temperature, close to 1,000 degrees Celsius, and then the particles start to adhere themselves. By the way, one more thing is when you saw the footprint of the Apollo astronaut on the sun, that material is just loose sand, okay, and the particles are just sticking to each other because of friction. So in sintering, what you do is you heat it at a very high temperature such that the bonding becomes very, very strong. It becomes particles migrate from atoms and molecules. So at the edge, they fuse together and they become bonded. We have reached strengths greater than 20 megapascal that way. I just told you the strength of a house brick, typical house brick is 5 to 20. So we have reached strengths greater than that with sintering. We have also done 3D printing, which still gives slightly weaker bricks, but it's good enough. We have used different type of binders. So we realized after when we used guar gum, we realized that, you don't have to use just bacteria. You can also use biological polymers, and that's giving very good results. So we've recently used biopolymers to construct bricks, and we have gone one more step further. We have till now all the bricks were being constructed in Earth-like environment in the lab, right? I mean, I cannot construct a moon-like environment in my lab. But then we made something called MARS. MARS stands for Martian Atmosphere Simulator, and here we make it vacuum, just like Martian vacuum. Mars has I can't recollect it off the top of my head, but about 100 times thinner or less pressure on its surface than Earth, 100 or more or something like that. So we create this vacuum, Martian-like atmosphere, fully carbon dioxide, and we make our brick in this small jars here. And we have made bricks with different type of materials, including now in Martian soil also. And we have seen that with biopolymers, they can use it for lunar and Martian regoliths and made into bricks. It is now available on bioRxiv, which is a preprint service. If you want, you can read the entire paper. But we have been able to make really, really strong bricks with that. Stronger than 20 megapascal. I mean, that is one of the strengths that we have. So by this time, we have, in the last 4 or 5 years, we have fully become masters of this particular of regolith handling and how to make structures with that. And we have done quite a bit of it. So we are now fully capable of making this kind of brick-like structures from 3D printing, through biopolymers, to bacterial polymers, to sintering, all these different techniques. And so where does it place us in terms of materials? By the way, the reason we are looking, why did we start with the lunar regolith? That's another question. I had initially said that the first human colonies had used the soil of that place to make these bricks. But why did they do that? Why did they use the soil that was there? Why not something else? Because that's the most abundant material that is there, right? And that's logical. For any long-term structure formation, you have to use whatever materials are locally available to you. Now, in the context of space technology, there is a technical name for this. It is called ISRO, which is a short form of in situ resource utilization. This idea promotes the use of local environments or local materials found in extraterrestrial environments. And regoliths of Moon and Mars have similarities and dissimilarities with the Earth soil. They're in some senses similar, but they're also quite dissimilar. Making bricks or consolidated structures. This is an important technology towards setting up extraterrestrial colonies. But this is only the first step. Okay, there are many other steps, many other technologies that have to be worked upon. For example, these bricks are also porous. Okay, so these bricks also have porous structures, so you can have air pass through from one end to the other. You can have porosities of the order of less than 10%, but it's still a very, very large amount of porosity. So to create colony-like structures or to create houses, you will probably need some kind of other structure, like an inflatable structure or something, and then protect this through another layer of bricks. So you need multiple technologies to build structures, okay, on the moon or the Mars, and there are many of these technologies that are still developing. So for example, this inflatable structure. These are being there's research going on in India. There's some very fantastic, interesting work going on in ISRO or in ISRO and other places. But still, we are still at the infancy of these technologies. By the way, it is instructive to place our space bricks in what is called as an Ashby chart. What you see on the left side, it's an Ashby chart. On the y-axis, you have a compressive strength, and on the x-axis, you have density. And these are different materials which fall into different places in this Ashby chart. The Ashby chart allows you to compare one material versus the other. Our space bricks initially started with quite a little bit of strength somewhere around here, and then now it has gone all the way here. So our space bricks occupy this area, and there are some harder than polymers. They are now harder than some of the earth bricks also, and this tells us this new type of material. It occupies a sort of a new place in the area of materials altogether. There's obviously a lot more interesting things from the perspective of materials, all of which I'm not able to talk about today. Time is limited, so I wanted to tell you about other things as well. We are working on other allied technologies for creating these habitats, including the space bricks and others. I am unable to talk about, some of our work is not published, so I will not talk about our work. That is why I took out publicly available work. This is the European Space Agency's Moon Village document. It is publicly available, so that's why I'm using it. You can also read it. You can get the entire PDF document for yourself. This is a very instructive document because European Space Agency did a full-fledged study, and this is not very old. This is 2020. This is still at a conceptual level, where they wanted to look at these different aspects of habitat creation. For example, deliver functional habitat features, define what the interior should look like, standardize different interfaces. These are some of the important things. Obviously, also assess potential in situ resource utilization. So you can see that others, including European space agencies, they are doing research on this topic right now. Much of the work that they are put into this document, they are still in progress. They are telling us about the technologies that will be necessary for creating that. So the document has some very nice renderings of settlements. Most of these technologies do not exist yet. They need to be created. So for example, here they are showing a sintered path, mobility path for rovers, which can be made through the sintering process that I was discussing about, of heating the lunar regolith to very, very high temperatures. There are other structures. And there's one more document here where you can see it says advanced phase ISRO structures. So these are the structures right here. This is a conceptual diagram, by the way. This doesn't exist. To create this kind of ISRO structures from so basically ISRO means that you will, the regolith that is out there, you will source that regolith and create these structures from there, the local material, right? So for that, you have to know how to make bricks from that. So that's where our space bricks technology comes in. ESA is also developing 3D printing technologies for the same. We are also developing that. There's multiple agencies all looking into 3D printing of Martian and lunar regolith also for the same thing. So there's a lot of interesting work that is going on. Okay, so till now I've been talking about structures outside, right? We've been talking about how to use the lunar regolith, how to create bricks, structures, etc. out of them. But we are on Earth. What do we do? How do we get sort of started on Earth. For that, what people have started doing, obviously you cannot do all experiments on the moon. You have to do some experiments here on the Earth before you can go out there. This idea of human research analogs or extraterrestrial analog sites has come up, where you take a site and you create a colony-like situation. And at the beginning, these are analog sites. For example, this is a site called Hera, which is being used in the Johnson Space Center, USA. It is a confined space where astronauts can train as if they are on the moon or Mars. In the beginning, these analog structures, by the way, there are two spellings of analog. This spelling is not correct. There is another spelling with an E. That's the proper spelling, but even in the quiz, you will see there are two spellings. It's the same thing here. We'll use each other, the analog GUE and the analog sort of interchangeably. In the beginning, when this analog research started, it was mainly for a study of isolation and confinement and remote conditions of a human crew. And for example, this can take 4 people and they can sustain themselves for 7 to 45 days, do different things. But now they are also starting to feel, we are realizing that these analog habitats can be used to test these different technologies also. For that, you have to make a much bigger analog and in a real physical place, right? So this this is a lab analog. This is sitting inside the NASA Space Center, and that cannot be used. We need realistic scenarios. I mean, and NASA has also done some of that. The one example of that is NEMO, which is the NASA Extreme Environment Missions Operations. And this is, you can see it is placed in a deep ocean. And this is obviously quite complicated. So we want to create designated lunar analog sites where we can test all these different technologies. Now, while we have test beds for rovers, etc., India does not have any designated lunar analog sites yet. Okay. And this is a bit of a problem. We need such sites. So one of the things I did, I mean, we went to Ladakh, we scouted that site. It's a fantastic place. I hope some of you have been there. If not, you will go there sometime. It's a fantastic place for trying out different technologies, using it as a test bed for these analog sites. So this is a picture of something called as a moon valley from Ladakh. It looks like the moon. Okay, this is Lamayuru. It is very close to Leh. It's a one-day trip, less than one-day trip from Leh and back. If you go to Leh, you can quickly go and come back to this place called Lamayuru, which is also in the local language, it means Moon Valley or something. There are many other geological features in Ladakh. For example, Ladakh is a cold desert, so you will find sand and the gravel and regolith type material here. And you can take a large piece of land there and use it to study or basically work on these different technologies. So we did that. We actually published this paper that Martian Lunar Analog Research Station in India, Ladakh is a potential site. These are my other authors, Dr. Binita and Group Captain Shumanshu Shukla, who is also the astronaut designate right now. So once we proposed this, this got quite a lot of attention in the news also. So we're quite happy about it. And this proposition was made last year. So this is last year summer that this article came out. And after this, I was very happy to see there was this very brave woman, Astha. What she has done is she has delivered India's first pilot project. It is not a full-fledged analog project yet, but she has done this project of building an analog site in Ladakh, and this you should have seen this. You'll be able to find news articles on this. So this was quite interesting to see. It's not long term, so it was taken and then it's been taken back. But we need to have more such experiments, and we need to have a designated place for doing these experiments in the future. So, I mean, we have to do so many different things, right? We have to develop all these different technologies, and we have to have these analog sites. But once we have these analog sites, we also have to transport these bacteria, etc., to the moon, and we have to do experiments there. How do we get started? And we have been doing some experiments. I'll not go into a lot of detail here. In space, to send bacteria, what people are doing is using lab-on-a-chip technologies, and this is one of the astronauts. You can see that in the International Space Station, there are so many experimental cubicles that are there. You can see all these experimental racks that are there behind the astronaut. And if the India's Bharatiya Antariksh Station comes up, it will be a very good opportunity for us to start biological experiments and biomanufacturing experiments in space. And we have been developing one such prototype in our lab, which is called MANAS. It's a acronym for microbial analysis in space. This is what one of our device looks like. You can see this is a 5 rupee coin. This is a chamber in which the bacteria grows. You can't see it. It is sealed, but there is an optical sensor here. There is another measurement device here, and the light goes through. You can measure the growth of the bacteria. This is the bacteria growing in our Manas chamber. The advantage of this Manas chamber is that it can be made into a small box, and it could be put onto Gaganyaan, or it could be put into another rocket and sent to the moon or sent to Mars or elsewhere. This is a paper that we had published. Again, this is a slightly old work. This is the version 1.0. It was published in Acta Astronautica. And since then, we have come a long way. We have made the full version of it. I don't want to go into, again, too much details about this because it's a slightly different topic. Now it's about taking some of these materials from Earth to the moon and Mars. This is a second generation that was prepared 2 years ago. Now we have a full small satellite version of this also ready that I'm not going to show you. We are still in the process of publication. This is what it looks like. It's a small device which can be held in the hand. That's how small it is. And you can put bacteria in here. You can send it up if anybody uses it, or if the bacteria can produce biopolymers, the astronauts can extract these biopolymers, put it with the moon brick and make their buildings, etc. Out there. So this is what we are hoping for. There's a lot of interesting opportunities that are there. This kind of building structures on the moon, etc. This requires a whole set of technologies. Okay, a lot of different technologies, which is going to require a lot of people working in a lot of different areas altogether. So the take-home message. The take-home message is make on moon. This is the most important thing. Just like make in India. Once we go to moon, we cannot. We have to depend on the resources available on the moon itself. Regolith is the most abundant material on the moon, and with that you can make brick-like structures. Bricks are these brittle structures. And as we saw, we looked at the compressive strength, which compressive strength is when you put this brick, sandwich it between two plates, and you compress it. And you apply a compressive force, and then you see at what strength it breaks. So that tells you how good the brick is. So we saw that we have been able to make bricks which are as good as Earth bricks and even better using our technologies. But this is just one aspect of the extraterrestrial habitat. There's so much more to do. We have to be able to build other structures which also participate in this. We have to build interior. We have to create interior designs. We have to look at so many different aspects all at once. So I think this is not a topic for just one person. This requires thousands of people over many years of work for this dream to be finalized. by the way, this is a cartoon somebody else made when our paper got published. It received a lot of interest from the news portal, so I thought it was quite funny. And obviously, some other cartoonist had made that. It was quite interesting to see. So with that, I think this is my research group. This is an old photo. This Rashmi and Nitin, who have done a lot of work, and now others are also doing it. Amog is here, who is also doing a lot of interesting work. Hopefully some of that gets published and we'll show you in the coming days. And these are all our funding agencies. We received a lot of funding from ISC, from ISRO, from the government of India, the Principal Scientific Advisor's Office, and DBT. So thanks to all of them for all the support. And yeah, so I'll conclude at this moment, and we can take questions.
We don't have any questions yet, but we can just wait for a few minutes, I think.
Sure. Okay, I can see some of the questions.
Yeah. Okay, so I think the first question is interesting. It is asking, the moon doesn't have atmosphere to grow microorganisms. Then how will the bacteria work on the moon, basically? And also we have UV radiations and other harmful such radiations. So have you thought about that?
Yes, that's a fantastic question. Thank you for that. I hope you have seen who is asking the question has seen the movie Martian. The astronaut has to grow potatoes and it has to grow. If you read the book, you know that he also had to grow bacteria in the soil. And the only way of doing that on either the moon or the Mars is to have a temporary greenhouse structure first, which has to be probably taken from Earth in the beginning. So the first colony will need a lot of support from Earth. Only then can the second generation can happen. So in the beginning itself, you can't take zero because it's such an extreme environment. You can't work with that. And then you have to provide some cover and some atmosphere for the crew to work, for some of these biological things to grow, plants to grow, for your own food, for the bacteria, etc. And that will also hopefully prevent radiation from coming in, and hopefully that's going to be important. Yeah, so the first civilization or the first settlement needs to set up something that is reasonable for the second, the second construction, the secondary generation of construction to begin.
The second question is by Urvi. It relates to the first one, but she's expanding on it by asking if there are any things that actually kill the bacteria or prevent the growth once it's there. So she's used bacteriocidal and bacteriostatic environments, if they're present on moon or not.
So first of all, bacteria is not present on the moon by itself. But once humans go, you will have to take this. Now, there are many different things in the actual environment that will be different from these lab experiments. Okay, so for example, we know that the lunar soil is charged, and that electrostatic charges exist, which can also kill bacteria. So this kind of bacteria, this kind of these things will have to. Not everything we can do in the lab. Some of this has to, as we understand the moon better and better, we'll have to incorporate some of them in the lab, and we'll see. But for the time being, we cannot replicate everything. You are right. There are issues on other issues that are there in the moon's environment, which cannot be taken care of, which has not been taken care of here. And yeah, the charge is one of that I can think of right away.
Sure. The next question is by Shrikant. he's asking, what are the potential advantages and disadvantages of building on the moon versus building on Earth's surface? Essentially, why are we doing this in the first place?
See, I mean, there is a very huge philosophical angle to that, including that whether we should ever become, should we remain confined to Earth or should we venture out? There are, if Earth is the only home we know, we have to take care of it. That's totally true. You see, when I started this research, I did not understand Earth much. I'm not a geologist. But one of the first things I realized that clay is what separates us from the moon. And clay is where all the life exists on Earth. That is the topsoil. You have to protect that topsoil for us not to become a desert and for us not to kill ourselves. So one aspect of a lot of this space research is also for us to understand our situation here better, understand why Earth is so special. The other thing is, of course, is you have to go out at some point because if any problem happens on Earth, we should have another colony to base out of. And I mean, humans are adventurous. We will go out at some point. So I mean, there's no disadvantage of that. You have to go out at some point.
Okay, the next question is by Urmi Srivastav. She's asking, could asteroid mining operations lead to the creation of hollowed out mobile space habitats or even asteroid cities?
It's possible. No, I mean, there is an issue with asteroids. Asteroids, the gravity is very weak. So when you start drilling in an asteroid, no, it breaks the asteroid immediately. And because there's no gravity, the asteroid doesn't stick to each other. So immediately you have a lot of dust, etc., that is produced, and then the structure itself breaks. And there is no integrity in the structure itself. So a lot of these asteroids, I mean, they remain together, not because they're stuck together well, but because they all have the same velocity, so they're not moving with respect to each other. But if you do mining, it's not that easy to create a hollowed out structure. You will break the entire structure. These are brittle objects, by the way. Even the space bricks that we're using, these are brittle objects. Asteroid is even more so. So when you mine on the asteroid, it is very likely that you'll destroy the asteroid and it will, go all over. Yes.
Okay, the next question is by Kauhar Bashir. Can the Chandrayaan-3 and the recent docking mission of ISRO help in building extraterrestrial structures on Moon? And how can they do that?
Yes, I mean, definitely. I mean, it's a very important experiment, the docking experiment. Later on, at least for the first set of first human settlement, you'll probably will not be able to send the entire structure there in one go. You'll have to send the structure in parts, and then the structures will have to dock in some orbit around the moon or on the surface of the moon. So that docking experiment is important for that also. So the first set of people that go there, they have to take the spacecraft and whatever they use, they have to use that as the first settlement. So and multiple of them will be required. So you're looking at a colony which is quite a few people over a long period of time.
Okay, we don't have any more questions, but I was just thinking I would ask a few so that it can help explain. So another thing was, do you also test the tensile strength of the bricks? Why or why not?
Yeah, so tensile strength can also be checked, which is as what Among is referring to. You apply tensile force and you check for the strength. Usually, when we make structures like our house, etc., almost most of the house, or sometimes the entirety of the house structure is under compressive loading. That's how it is made. So the compressive loading is more important. And for things like concrete, the compressive strength is far more than the tensile strength. So it can bear a lot more load under compressive strength than under tensile strength. So we want to make the structures in a way, these brittle structures have more strength in the compressive state. So we want to make the structures such that everything is under compression.
Yeah, I think we don't have any more questions. Maybe we can wait for a few minutes.
Dr. Praveen, should we conclude or wait?
I think, yeah, since we can't see many other questions from these participants through e-class platform. So maybe I think if anybody is having any further doubts, they can contact the speaker, provided email is shared, or how to contact them. That information you may share so that.
Sure. Yeah, my email is very simple. It is my name, Aloke Kumar, ALOKEKUMR @isc.ac.in. So if you have anything you want to reach out to me, you're definitely more than welcome.
Okay, good. Okay, Sri Amoga, this is a very, well you have moderated. So thank you so much. And also our sincere thanks to Professor Aloke for providing a very informative lecture, and you have explained the things in a very, as if a school teacher is explaining to students. In that way you have explained. Thank you so much. And also supporting our START program.
Thank you. Thank you, Dr. Praveen. Thank you.
Thank you, Dr. Praveen.
With this, we are completing today's session, and will be joining back on tomorrow, 3:30 p.m. Goodbye, and meet you all on tomorrow.